Okay, hi everyone. I guess it's time so we can get started. And I hope things are going along well with your final project and that you had a good Thanksgiving break also. So this time I'll be talking about models with latent random variables, with the idea that these are models that can allow you to do some interesting things that you aren't easily able to do with the models that I introduced previously. So we can just jump right in. And previously we talked about discriminative versus generative models. I think maybe even in the very first class or second class that we had here. And a discriminative model, as we all remember, calculates the probability of the output given the input, like probability of y given x. Whereas a generative model calculates the probability of a variable, px, or multiple variables, like a joint probability, pxy. And if we think about which of the models are discriminative versus generative, let's say we have a BERT-based part of speech tagger with independent predictions. Any idea about that? Basically, it predicts each output. Yeah, discriminative, right. What about an encoder-decoder based part of speech tagger? So it takes in, yeah, discriminative. It takes in an input and calculates the probability of the output. Now the probability of all the output variables are intertwined as opposed to being independent, but it's still, a discriminative model. And the language model is a generative model, right? So interestingly, people talk a lot about generative AI nowadays, but actually a lot of generative AI models are discriminative models, like stable diffusion and stuff like that, but we'll forgive them. So types of variables. This is an important distinction that we are going to be talking a lot about in this class. And there's different types of variables that we can be talking about. There's observed variables versus latent variables. And the difference between these is basically observed variables are something that we can see directly from our data. These could be, for example, the inputs, or in a labeled data set, they could be the outputs. And a latent variable is usually a variable that we assume exists, but we aren't given the value of this variable. There's also an idea of deterministic variables versus random variables, where a deterministic variable is a variable that's calculated directly according to some deterministic function. So basically, you take one variable in, you get another variable out, and you'll get the same variable all the time. Whereas a random variable, which is also called a stochastic variable, is a variable that obeys a probability distribution and may take any of several values, of several or infinite values. And so just to test the understanding here, let's say we have an attentional sequence model using LSTM-based attention or transformer, whatever we want. It's trained using maximum likelihood estimation and teacher forcing. Are the following variables observed or latent, and are they deterministic or random? So let's say we have the input word IDs. I wrote them F here, but it could be X also. Any ideas? Observed and deterministic, yes. What about the encoder hidden states? Yeah, latent and deterministic. What about the attention values? Also latent and deterministic or random? Yeah, deterministic, exactly. So this is a little bit of a tricky one because the attention values look like a probability distribution, but actually they're not. We never do sampling from them. We never explicitly treat them as a probability. So essentially, they're just deterministic variables that are used to mix together other deterministic variables. And then the output word IDs, E. observed and deterministic, or at least at training time, they're definitely observed, right? And then at test time, you could treat them as latent variables in some cases, but yeah. And these are not deterministic, these are random variables. And the reason why they're random variables is because we're calculating a probability over them. We can do things like sample over them. Very often we'll be sampling a whole bunch of outputs. So these are the things that we're actually trying to model the probability of. If we were using a different method, a non-probabilistic method of modeling the output distribution, like let's say we're training like a margin-based model, then arguably these could, not be probabilistic variables because we don't have a specific idea of probability there. Is this clear? Any questions? And the reason why this is important is because we can only do certain things with respect to random variables, certain learning algorithms are only applicable to random variables. So we should have that idea in our head. Okay, so latent variable models. A latent variable model, specifically a latent variable model over probabilistic variables, is a probability distribution over two sets of variables, one being observed and one being not observed. So the X variables are the data that we've seen, and the Z variables are the data that we have not seen, but we're trying to model probabilistically. And so I should say Z are latent random variables in this case. And there are a lot of different types of latent variables that we could be using. One example is latent continuous vectors, and an example of this is something called variational autoencoders, which I'll be talking about in a moment. They can also be latent discrete vectors. The most common example of this is something like a topic model, which we haven't covered in this class, but I can cover briefly, and then we can cover, you might have heard of it in other places. And then there's also latent structured variables. So these can be latent sequences over each tag over each token in the input, or it could be like latent tree structures or something like this. So I'll talk about each of these in turn. I had one question on Zoom, which is if we set a threshold to choose the label from a probability, will it be a deterministic variable? So a deterministic variable is basically where you get a particular input and you always get a particular output. So another way to look at a deterministic variable actually is if we have some input and the probability of let's say this is A. In this particular case, Y is a deterministic variable where its value is always A, right? So another way to think of deterministic variables is they're kind of like random variables where the probability of one value is 1 and the probability of all the other values is 0. Cool. So the kind of a very nice method for learning latent variable models that works well with neural networks and can be expanded in a lot of different ways is something called variational autoencoders. And variational autoencoders are a latent variable model that looks a little bit like this. We assume that we have an observed output. We have an observed output X, or we actually have n observed outputs X. And then we have a latent variable. And the latent variable, usually we assume that this latent variable was drawn from a Gaussian distribution with 0 mean and unit variance. And then we have the parameters of the model. And then we calculate the probability of the output given this latent variable and the parameters of the model here. And So usually this function f, yes, sorry. And we have a function f that actually maps directly from the latent variable to the output here. If you're not familiar with this, this kind of like diagram, this is something that's used pretty widely in kind of like probabilistic models or probabilistic graphical models, where it's basically saying that you just repeat this process n times. So you have n data examples and you have a process that looks like this. And here is an example. So we have some complex distribution over here. And this complex distribution is essentially characterized by a Gaussian distribution over the latent variables and a deterministic mapping function that maps from the variable in latent space z to the output x. And the reason why this is interesting is actually it's maybe easier to think in continuous space when you're thinking about these, but essentially you can take this Gaussian space here and arbitrarily transform it to get any other kind of complicated distribution over here. So it could be a Gaussian mapping to like a circle, or it could be a Gaussian mapping to like all natural images in the world or something like this. So this distribution over X could be kind of like arbitrarily complicated. And if we're talking about natural language processing, this distribution also doesn't necessarily need to be continuous. It could be the distribution over all of the sentences in the world or something like that as well. So it doesn't really matter whether this is continuous or discrete or how complicated it is. We can always come up with this mapping function. Are there any questions about this so far? No? Okay, I'll go on into the details now. So basically what we do is for each data point, we draw latent variables according to this prior probability. And then we can also draw a data point according to this, this posterior probability here. And the joint probability distribution over the data and the latent variables looks a little bit like this. Just, by the chain rule. And once we have this probabilistic perspective, also we can calculate a loss function that maximizes the probability of the data that we're trying to model. So specifically, we'd like to maximize the log likelihood of the data we're observing, just like we maximize the log likelihood of the data we observe when we train a normal non-latent variable language model. And here's an example. So like right now, we're assuming we just have a generative model over inputs. And so we sum the log probability of all of the inputs, and we try to get the probability of the whole corpus here. Now, for a single example, note that we don't have z anywhere in here. For a single example, the marginal likelihood, in other words, the likelihood considering all possible assignments of a latent variable, is essentially the integral over all possible latent variable assignments, multiplying the prior probability by the posterior probability here, or by the generative probability here, and that gives us the probability that we had over here. And so actually, just to make this completely clear, the right side of this equation is also equal to this, basically, and like from statistics, we know that integrating over the joint probability gives you the actual probability of just one variable. So that's why that's equal. We can also approximate this by sampling z's and summing over them. So essentially, instead of trying to take this whole integral, which is, obviously, if it's a relatively complicated distribution, it's not feasible to do this because, we can't solve this integral in closed form. Instead, what we can do is we can sample from, here we go. We can sample z from the prior and approximate this integral up here. And if we take an infinite number of samples, these two are guaranteed to be the same. These two values are guaranteed to be the same, which is kind of a fundamental property of statistics. However, we can never take an infinite number of samples, right? So the problem here is that we might not be taking an infinite number of samples. And so this estimate of the probability may be inaccurate. In particular, if we go back to the example that I showed before, let's say essentially this sample over here maps to giving a high probability to this space over here. Let's say we sampled 10 points from the prior. If we sampled 10 points from the prior, maybe we get one here, 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 one here. And if we do that, we don't get any samples that assign a high probability to this point, even though this point has a relatively high probability according to the distribution. And so just because we didn't manage to sample an appropriate point from the prior, we're going to be assigning the output in unfairly low probability. So that's a real problem, and essentially will cause us to underestimate the probability of actual high probability examples quite frequently. So what do we do? What we do is we essentially can take a method called variational inference. And what variational inference does, or what we can use the variational autoencoder, which is a type of variational inference. And so what we want to do is we want to learn this model in an efficient way. So the first thing, there's two tasks of interest that we would like to do. We'd like to learn the parameters of this probability of x given z. And another thing that we'd like to do is we'd like to do inference over z with this distribution, basically the probability of z given x. So given x, what are the high probability values of z? And the reason why this is useful is essentially, going back to our example again, instead of randomly sampling 10 examples from this prior distribution, using them to approximate our probability, what we can do is we can essentially have a reverse model that goes from x and predicts a high probability z. And then we can use the high probability z to essentially effectively estimate the probability of x. So we go like x to z, find all of the samples over here that are kind of like in the high probability space, and then use that to get the probability of x, and that reduces the variance of our estimate of the probability of x. Yeah.
Can you go to the slides?
The one that I just showed, or?
This one is not the one.
Okay.
In the summation thing, shouldn't you also multiply like probability of z, like the probability of actually observing z?
Yeah, very good question. So the question was essentially, in this sum over here, should I multiply in the probability of observing z? And actually the answer is no. When you're sampling according to z, it might be easier to see in discrete space. But let's say we have a probability distribution that looks like this. the probability of Z equals A is equal to 0.75, and the probability of Z equals B is equal to 0.25. Let's say we were taking the integral over this, which is essentially summing over all of them. That would be P Z equals I P of X given Z. And then I equals, or I N A B. And so basically you'd be multiplying 0.75 and 0.25. However, if you sampled according to this probability distribution, essentially you would get A 3 times for every time you get B. And so because of that, essentially you get A 3 times. So that's like multiplying by 0.75.
But then the more points we sample, the more Z's we sample, we're gonna get a hard probability, right? The more things we sum over when we.
Oh yes, sorry. I have a mistake in this equation. So thank you for asking. This should be preceded by the dividing by the size of the sample. So we always divide by the size of the sample when we do this. Yeah. I've presented these slides like multiple times and never noticed this. So sorry. Thanks for asking the question, and I'll fix it next time. Yeah, any other questions before I move on? Let me just take a note. If I don't take a note now, I'm not going to remember in 1 year. So, okay, great.
There's a chat.
Okay. Where do we use this formalism of modeling X through a latent variable? Yeah, so I'll get to some actual examples of this later. So yeah, anyway, modeling this is intractable. And so basically, what variational inference does is it approximates the posterior. It approximates the posterior of the latent variable given X with something, it says here with a family of distributions, but basically it approximates it with another model. It learns another model that allows us to approximate this posterior. And so this is a little bit detailed. I'll try to explain it briefly, and you can read the very nice tutorial that I have in the recommended reading if you want to go into this more. But basically, what we want to do is variational inference approximates the true posterior with a family of distributions. And so we want to learn essentially an approximation of the actual posterior distribution given approximated according to a model. And the reason why we don't learn this directly is because we don't know what the actual latent variables are, of course. So we can't just do supervised learning to try to learn this model. And what we do is we use something called the variational lower bound, where the variational lower bound is essentially the lower bound between this KL divergence here and the log probability of X. So this is what we actually want to model. And this is something that we cannot model directly, but we can transform it in a couple ways to make it close to what we want to model. And specifically, the thing that we can do is we can take the expectation of the variables that are sampled according to this this model here. Actually, this model here, Q, is called the inference network, normally when we model it using a neural network. So I'll just call this this Q phi Z of Z given X, the inference network. And then we calculate the log probability of X given Z. And then we also have this regularization term that tries to regularize the probability of the inference network to be close to the actual prior probability. And essentially this elbow term here, it upper bounds the log probability. So if we're pushing down, it lower bounds the log probability. So if we're pushing up this elbow term, we're also pushing up the log probability of the data. So, or we're pushing up the lower bound of the log probability of the data. So we know that the log probability is no worse than this elbow term here. So practically, I always like to give examples. So before, again, I had this example here. So what we do is, given this X term here, we take our existing inference network and we sample several latent variables, either one or several latent variables from the inference network. Maybe they would all concentrate around the actual high probability latent variable here. And then we calculate the log probability of the actual example given these latent variables. And that's the left-hand side of the equation that I just talked about. The right-hand side of the equation that I just talked about is a regularizer that tries to prevent the inference network from moving too far away from the prior probability. And so if the prior probability is a zero mean and unit variance Gaussian, if our inference network tends to pick things that are like let's say our inference network predicted something that's kind of close to this Gaussian, it wouldn't be penalized very heavily. If our inference network predicted something like way out here, it would be penalized heavily because this distribution is very different than the actual prior probability. So basically what we have is we have two different conflicting objectives. One objective is trying to maximize the probability of the point given the distribution the inference network predicted over the latent variables. And the other term is basically trying to make the inference network's prediction over the latent variables be similar to the prior. And these two kind of push against each other. So that's kind of the high level idea. Are there any questions about this? Okay, and as I said, the tutorial that I linked in the on the page is very nice, so you can go ahead with that and look at that for more details. So yeah, maybe I'll just skip over these two things. So yeah, like as I said before, this can kind of be viewed as a regularized autoencoder, and a normal non-variational autoencoder could also do something similar. So a normal autoencoder, basically what it does is it might take an image. Can amaze everyone with my art skills here again. And it would take an image and do a deterministic mapping into this variable here, maybe a hidden continuous vector or something like this. And then it would map back to try to reconstruct the image. And this is, a pretty common way of learning like latent vectors or other things like this. However, it's missing a few of the nice features of the variational autoencoder. And basically, the biggest feature, if we didn't have the scale regularization term, is essentially now we have no prior over the input. We're assuming no prior over the input, which means that a couple things. So first, the autoencoder, we have no way of knowing what the distribution here is going to look like because we have no prior over the input. Another thing is that a regular autoencoder is not a generative model. It's not a model where we could sample new examples, X, from this model. It's just basically, it's essentially a good way of learning latent vectors here, but it cannot function as like a language model or a model of images or something like that. You also can't compute the log likelihood of the data X, because in order to calculate an autoencoder, you have to take X, you deterministically find this variable here, and then you output this variable here. But there's no way of calculating the log probability. So you can think of like essentially VAE is a probabilistic model. Autoencoder may be good for learning latent representations, but it's not a probabilistic model. Are there any clarification or? Okay, cool. So how do we learn this model? One problem is if we learn this model in the kind of standard way or the kind of like most straightforward way, essentially we would have trouble learning it because we need to do sampling within the model. And the reason why we need to do sampling is essentially we have a encoder or an inference network that would predict the mean and the variance of the probability, the posterior probability distribution over the latent variables. And then we could sample multiple examples from this probability distribution and use that to train the decoder network. But as I mentioned in the last class, sampling and training models is very unstable because like, you know, maybe you just get not enough samples that give a high probability, or the samples that you get don't happen to be good ones for training the model. So in general, if at all possible, you kind of want to avoid sampling in your model, although you can avoid it some of the time. So there's a really neat trick that people have used for variational autoencoders, which is called the reparameterization trick. And what it does is it notes that normally when we learn the inference network, we learn this by predicting the mean and covariance matrix of a Gaussian, and then use that as our posterior probability over the latent variables. And instead, we take advantage of the fact that you can also sample from a Gaussian by sampling from a zero mean and unit variance Gaussian, then multiplying the value by the covariance matrix and adding the mean. And that also gives you a sample from the same Gaussian. So essentially, this procedure and this procedure will give you the same result for both of these values. But in this case, now you can backprop all the way through the model because the sampling is not essentially intervening in your computation graph. So if you have sampling in the middle of a computation graph, sampling is non-differentiable. So it essentially, you can't backprop through it easily, but in this case, you can backprop through it easily. So this is a really useful trick. This is the reason why essentially variational autoencoders became popular, because it makes it much easier to train. So to give an example, I've given a few examples already, but this is an example of a latent variable model. And generating from, normally when we generate from language models, we can use ancestral sampling to just like generate an output sentence, right? So we calculate the probability of the next word, and the probability of the next token, and while the next token is not the sentence end token, then we can just sample the next word. And also, of course, we can do a conditioned language model for like translation or other things like this. And this paper, Generating Sentences from a Continuous Space, essentially what it does is it takes these language models and it also adds a latent variable in them. And So essentially, we have a latent variable Z that generates the output. And it's like an encoder-decoder model, but the latent representation is a latent random continuous variable or continuous vector. Essentially, the input and the output models are identical, or maybe a better way to put it is the sequence encoding model is essentially the same. So we have a sentence encoder, and that generates this latent variable Z. And then we have a sentence decoder that generates conditioned on this latent variable Z. And so this is relatively simple. You could just take transformers and use a transformer model to predict a vector, and then use a transformer model conditioned on a predicted vector. Yeah.
One thing that I would like to maybe add is that the Z has to have like a lower dimension than X, right? Because then if not, then Z can just be like an identity thing to X, and like it'll be trivial.
So this is a good point. The point was Z has to have a lower dimension than X because otherwise it could be an identity and it would just be trivial. That's not actually true completely in the case of a variational autoencoder, because a variational autoencoder puts a prior over the latent variable Z. And if your original X doesn't follow that prior, then it still needs to learn the mapping between the original space, like space of X, to a space of Z that matches the prior. And I'm actually going to give an example of that later, which is kind of a clever example, and it's a nice way of using the prior in a clever way. So the motivation for latent variables within this generative model, like one question you might ask is, why don't we just like train a regular language model and not think about latent variable Z at all? So there's a few motivations. The first motivation is that this might allow for a consistent latent space of sentence vectors. And so this is a standard encoder-decoder where basically it was the autoencoder with no prior. And then we had the VAE. And when we had the standard encoder-decoder, like one thing that might happen in a standard encoder-decoder is we might have a latent space that looks a little bit like this. So we have like a lot of points up here and a lot of points up here. And then this is really sparse in here. And there's no, like, essentially the sentences generated from the middle would not be natural sentences, or the representation there is not very natural. So what they actually tried to do was train a standard encoder-decoder and then take two sentences and try to interpolate between them. So basically they move the representation from one to another. And here you can see it starts out with, I went to the store to buy some groceries, and ends up with horses are my favorite animal. And in the middle, it's like horses are to buy any groceries, or horses are to buy any animal, kind of like unnatural sentences in the middle. Whereas here, it starts out with like, I want to talk to you, and she didn't want to be with him. And it kind of goes like in natural order between these sentences, and all the ones in the middle are also consistent. And the reason why this would happen is, because like essentially we're guaranteed to have this kind of dense space of embeddings. Like the prior encourages the space of underlying embeddings to be dense. And so none of the ones in this interpolation would be like unnatural, I guess. Another thing is like for sentence embedding models, this could be more robust to noise, and VAEs can kind of be viewed as a standard model with regularization on top. So there are some difficulties in training VAEs. One difficulty is that of the two components in the VAE objective, the KL divergence term is much easier to learn. And the reason why the KL divergence term, that's the term that I had on the right side that regularizes the inference network to be close to the prior. Oh, sorry, I have a question on Zoom. So how did they generate the intermediate sentences in the interpolation experiment? Yeah, sorry, I can explain this a little bit more. So basically what they did was they took the inference network and they used the inference network to essentially generate the mean from sentence number 1. They used the inference network to generate the mean from sentence number 2. And then they just like took mean of sentence 1 times 0.75, mean of sentence 2 times 0.25. So they basically just like linearly interpolated between the two vectors. Yeah, so essentially on the left side here, this requires a good generative model. So this requires your model to actually be able to generate your outputs X. However, for the right side, all you need to do is you need to set the mean and variance to be the same as the prior. So you need to set the mean to be 0 and the variance to be 1, and you get something exactly the same as the prior, and the scale divergence term goes to 0. So the problem is, like right at the very beginning of training, when you don't yet have a good generative model, this gets optimized, and then you essentially have something called posterior collapse, which results in the model learning to rely solely on the decoder and like not and ignore the latent variables here. So there's a bunch of like little tricks that people use to fix this problem. One is KL divergence annealing, and the idea is multiplying the KL term by a constant lambda starting at 0 and then gradually increasing to 1. And the result is that the model can learn to use Z before getting penalized. And so this KL term weight starts out at 0, and then they anneal it to 1, and then train just with the KL divergence term at 1. And what you can see here is like right at the very beginning of training, the model basically learns to ignore the scale term and just learn good latent representations, kind of like a standard autoencoder model. But then when you introduce the KL term again, it kind of optimizes the KL, or it kind of lowers the KL. And then as you continue training, the KL gradually goes up again as you're like learning the generative model better that uses the latent variables. So this is one way. Another way is this is called free bits, and basically what it does is it limits the effect of the KL term to a particular value, and basically says you get a certain number of like bits of information about the latent variable for free before you start paying the prior here. So that's another method. Another thing you can do is weaken the decoder. I actually don't recommend you do that. So I'll skip that part. And then another thing is aggressive inference network learning. And basically this is a little bit, it's a little bit similar to the idea of like, of weakening the KL term at first. But basically what you do is you take more steps on learning the inference network. So you take more steps on learning the inference network first before updating the decoder. And what that does, what that essentially does is like you might take 10 steps on the inference network and then 1 step on updating the decoder. And the reason why this is good is because like right at the very beginning, the decoder is kind of like dissociated from the actual latent variables. It's like learning to do well without using the latent variables at all. And this essentially encourages the inference network to learn good latent variables, which makes it easier for the decoder to use them. So these are all methods that you can apply to solve this problem. So yeah, up until this point, this was all kind of like variational autoencoder stuff that could be for NLP, or it could be for images, or it could be for anything else. I think where it gets really interesting is when we start talking about more interesting latent variables which is what I'm going to be talking about next. But are there any questions about the part up until this point? Okay. So discrete latent variables. Up until now, I was talking about a continuous latent variable, like just a vector of continuous numbers, like a sentence embedding or something. So a lot of different ways you could handle discrete latent variables are things like part of speech of a word, or class of a question, or like, let's say you're modeling handwriting, you could also model the traits of the person who is writing it. Like, are they right-handed or left-handed or something like this? And so how do we handle these? The problem here is that we can no longer easily use the reparameterization trick that we had before, because we no longer have a Gaussian prior. And essentially, we can't use this reparameterization trick, so we're kind of stuck with respect to training the model. So one way that we can handle this is through enumeration. So essentially, if we have discrete variables, like the reason why we needed the reparameterization trick and sampling in the first place was because we had an integral, and it was hard to model the integral in closed form. So now our integral is a sum over some discrete latent variable z. And if that sum is small enough, we can just enumerate all of the values, right? So we just enumerate and calculate this probability, and we're done. However, in most interesting cases, that's not going to be the case. We're going to have a very large number of variables. And so we can also randomly sample a subset of configurations of Z and optimize with respect to the subset. There's various flavors of this. All of these are essentially similar to the things that I talked about in the last class. So we can use a reinforcement learning style thing like policy gradient or reinforce to try to learn these. Another thing that we could do, although it gives you a biased estimator, is just sample them and then pretend like those are the only variables that exist, and just sum and maximize this value here. So there's a lot of different ways that you could do this as well. We can refer to the previous class. But the maybe more interesting thing is that there are also reparameterization tricks for discrete variables, like we had for the latent continuous variable. Unlike the reparameterization trick for the Gaussian, these are all approximations, so they don't give you the actual value that you want, but they do allow you to approximate. So the normal way that we could be doing sampling to do an approximation is something like this. So essentially, we have a probability, and we do a categorical sampling operation over this probability. So basically, we sample one of the variables according to this. The reparameterization trick essentially looks like this. And so what we do is we take the log probability, and we add something called the Gumball distribution here, and take the maximum value. And this is similar to the reparameterization trick. This is similar to the reparameterization trick in the Gaussian, in that this will give you the actual, these two things will give you exactly the same result. In the limit, this will give you a sample according to the actual probability distribution. This will also give you a sample according to the probability distribution. And this isn't super important, but this is what the Gumball distribution looks like. It's basically the negative log of the uniform distribution between 0 and 1. And if you take this, then that will essentially make the categorical sample in this value here be the same. However, there's still a problem training with this reparameterized method. Anybody know which function you definitely don't want in the middle of training your neural network in this here. Argmax, yeah, exactly. So you don't want an argmax in your in training of a neural network because an argmax is non-differentiable. So unlike the reparameterization trick and the Gaussian, where basically all of the operations that we were doing were like multiplication and addition and other like differentiable operations, now we have an argmax in here, and that causes problems. So because of this, there's an approximation to the Gumball argmax, which is called the Gumball Softmax. And this is a way to soften the decision and allow for continuous gradients. And it's as simple as this. So instead of the softmax, we take the argmax. Instead of the argmax, we take the softmax. And in addition, we have this temperature term tau here, which allows us to soften or like essentially make the distribution more or less peaky. And this is a good example here. We have the categorical distribution, which might look a little bit like this. And if we set the temperature to 1, essentially the Gumball softmax will pretty closely match the categorical distribution. Or if we take an infinite number of samples, it will match the categorical distribution. Then if we take samples with and then if we flatten it out, it will become more flat. And so essentially one thing that we can do is we could gradually go from having a relatively high temperature to having a low temperature, which allows us to essentially start out with a smooth distribution that's easy to optimize, and then gradually work our way towards actually optimizing something that looks pretty close to this argmax here. And of course, we're going to be using this Z in a downstream model. So actually having the most probable Z is not a bad idea. So essentially, this is what we can one thing that we can do. So this is pretty cool. If you're interested in this, the paper is written relatively well, so you can take a look at the paper too. So question or?
Can you explain what the Gumball is again? Like,
Yeah, so the Gumball function is a special function that basically just like we can reparameterize a Gaussian by taking a zero mean and unit variance Gaussian and then multiplying the covariance and adding the mean. Or if we do that, we can go from a Gaussian zero mean unit variance Gaussian to the actual distribution we want to model. We can do the same thing by doing like Gumball, by taking this Gumball distribution, adding it to the log probability here and taking the argmax. And so now the whole idea of reparameterization is basically we don't want to be doing sampling in the beginning. We don't want to be doing sampling in the middle of the computation graph. So we move all the sampling to the very beginning of the computation graph before we've calculated anything else. And so we're doing the same thing here. Here, the sampling is not dependent on any other thing we calculated. So the Gumball distribution just happens to be the distribution that allows you to do this in the case of categorical variables. And it happens to be negative log uniform 1. If you want to go through and do the derivation to see why that's the case, you can do that. I'm not going to do it here, but yeah. Cool. So now I'd like to talk about some application examples in NLP. And I think this is actually where this gets most interesting because it demonstrates how you can be creative, maybe more creative than people have been in like image processing or other things like this. And just to give one example, you can use a symbol sequence as a latent variable. And so here we have an encoder decoder with a sequence of latent symbols. And so we have a input S1 through 4, and then a latent sequence C1 through 3, and then we reconstruct the output S1 through 4. And essentially what this is doing is this has been used for summarization, for example. And so what you try to do is you try to take a long sequence, generate a short sequence of latent variables, and then reconstruct the long sequence. And the way you do this is you do this, get to you in a second. The way you do this is you do this by sampling essentially outputs from the model, sampling outputs from the model, and then you put a prior over the values here to maybe look like summaries or just like look like English or something. And in particular, they use a model that has a copy mechanism incorporated in the model. And because the model has a copy mechanism incorporated in the model, it's more likely to copy things from the input than not copy things from the input. And so basically having those two inductive biases, one based on the encoder-decoder model and the other one being the prior on the latent variables being equal to like being natural English, that allows them to learn a summarization model very lightly supervised or not supervised at all. So, yeah.
So how is this different from like stacking one hidden representation? That's like you have a sequence of latent variables. How is it different from like inferring it with like one step rather than a sequence?
So this is a great question. So how is this? Here we have a sequence of embeddings, right? C1, C2, C3. And how is that different from just stacking H1, H2, and H3 and learning a variational autoencoder over this? So there's three differences. One difference is just how you make the predictions. So these predictions are made autoregressively with encoder-decoder models. So normally what we would do is we would just learn the mean in covariance of this like big vector, but here they're learning it with in autoregressive models. So like inductive bias of the model architecture is one difference. Number two, they have a prior over a language model prior. So basically they have PC. Could also call this like, it's probably better to call this Z1, Z2, and Z3 because these are the latent variables.
So what is the prior over Z here?
It's a language model.
Okay.
So they have a prior to make the latent variables look like natural language. So that's difference number two. Difference number three is this is variable length. So they also predict the end of sentence symbol to decide when to finish. And because of that, here, if you were just predicting one big stack at a time, you'd probably fix the size. Yeah,
it wasn't clear that it's variable.
Yeah, it's not very clear from this. So yeah, that's why I said it's a great question, but those are the three differences. Yeah. You could also think of interesting things where you take advantage of the fact that those are kind of like similar and somehow like.
How do you do inference here of the latest sequence?
Yeah, so in this particular case, they just trained this using reinforce. So they sampled sequences from the encoder-decoder model and then generated the outputs. They didn't. In this particular paper, I don't think they used like Gumball Softmax or anything like that, but there are other papers that use like Gumball Softmax to do the inference there too. In the case that you would use a Gumball Softmax, you could actually just interpolate. You could interpolate the embeddings. So you would take this distribution and interpolate the embeddings according to that distribution here. And that would actually allow this to be end-to-end differentiable. And you might finish generating when the end of sequence symbol had a higher probability than any of the others or something like that. So that's another option. So there's also the idea of something called emergent language. And so emergent language, essentially what it is people try to learn language as a latent variable where you have an input and an output. And just to give one example, you might take an image and try to convert this into a sequence of latent discrete symbols, and then take the sequence of latent discrete symbols and re-predict the image using a decoder. And basically what you're doing is you're taking this image and you're forcing it to convert it into discrete symbols. So you kind of need to encode the image in a appropriate way using something that looks a little bit like language, because language is a sequence of symbols. I think this is interesting kind of academically. I think it's maybe like also, there are papers that say this doesn't work very well because it doesn't a lot of the time, or at least if you do it in naive ways. I think this is interesting. I think it might be even more interesting from the point of view of like language change as opposed to language adaptation, rather than like learning language from zero, because in reality, like in the world, it's very rare that people learn language from zero. Usually like you learn it from your parents or something like this. Yeah.
Well, also there's a long-term discussion among psycholinguists that you don't hear enough language to actually learn it. And so there's a lot of people think that there's some intrinsic things built into the human brain that constrain the possibility. I don't know if that's too often.
Yeah, so there's the point that Bob made is basically like there's some argument that or some linguists basically contend that we don't learn enough language to actually learn it from the input that we get. It's called the poverty of the stimulus. It's an argument called the poverty of the stimulus, and some people argue that essentially we have to have some intrinsic wiring to allow us to learn language in our brain in order to learn as efficiently as we do. I'm not sure if I actually entirely buy that.
I didn't used to believe it, but I do now.
Okay.
And the argument is that there's some arbitrary structures in the brain because everybody's human, they have the same arbitrary structures, and that gives us a bias that looks at this.
Yeah, so and what Bob said is essentially there's some arbitrary structures in the brain, and because we have those structures, that gives us an inductive bias to learn language in a particular way. Yeah, I'm happy to talk about that more. So this is a paper that How, one of the TAs for this class, and we did. I didn't put this on the slides, but I think this is kind of a maybe interesting example of this. And basically this is doing, this paper is doing quote unquote emergent communication, but we're starting out from kind of having some idea of like what language looks like, and then adapting to the person that we're communicating with to try to match the way that, like essentially, like let's say we're talking about an image referential game task or something like this, where we need to pick an image based on the language here. It will try a whole bunch of different ways of explaining the image, and then it will gradually adapt to the ones that are most like useful for solving the task. So I think this is also maybe an interesting way of using these sorts of latent variable models.
Also the other way around, where emergent communication as a determining scheme helps NLP helps learn natural language better.
Okay, yeah, and there was a comment that there's actually the other way around, which is emergent language acquisition as a pre-training scheme helps models learn language better. So yeah, if you have references for that, we could show it. So there's also kind of unsupervised methods for learning structure of language. And this particular example is something called unsupervised recurrent neural network grammars. The basic idea is we are learning, I actually don't think I was here for this class. You talked about CFGs.
Yeah.
Yeah. So basically this is learning a CFG, a context-free grammar, as a latent variable. And the way it works is it's rather clever. It essentially predicts it takes in the sentence itself as X, and then it predicts the probabilities of this grammar is Z. So it predicts the probability distributions of the context-free grammar is Z. And then it parses the sentence, and that allows you to learn better underlying structure. Another example that we have here is essentially kind of semi-supervised learning for semantic parsing. And semantic parsing is essentially going from language to some sort of language to some sort of underlying semantic representation. One example of this being semantic like code or question answering programs or something like this. And essentially what this paper does is it learns a language to code generator in a supervised way, but then also in an unsupervised way, it has the inference network that predicts the underlying program, and then it has a reconstruction loss that tries to repredict the original utterance. And you can use this as a semi-supervised objective. And so basically, one other thing that I didn't mention in this one, which I think is another interesting use case, which kind of goes with the comment before where we were talking about how the underlying vector needs to be smaller. The latent vector needs to be smaller than the input in order to learn compression. One example of something where you can do of an application where you can do something interesting despite the fact that that's not the case is unsupervised sequence modeling or unsupervised translation. So if that's the case, you can have the input be English. So you have like English 1, English 2, English 3. And you can have the output be French. French 1, French 2, French 3. And then you have your inference network predicts Y given X. And your reconstruction network predict X given Y. But you might have lots of unsupervised text or monolingual text in French that you could also use to learn the prior over French text. And so by doing this, essentially, you can learn a model that does either in an unsupervised fashion or a semi-supervised fashion, does translation between two languages. But you can incorporate, basically a very large amount of monolingual data in training this model. And so this is a paper where we did that. And so basically this paper does this over a whole bunch of different kind of like sequence tasks. Like we do unsupervised translation, we do style transfer between different styles, and we do kind of like also decipherment. So like taking a cipher and reversing the cipher. And the interesting thing about this is we demonstrate, why having this prior is useful and why having this probabilistic interpretation is better than other heuristics that you could be using. So if that sounds interesting, you could try that as well. Yeah. So that's basically all I have for today. Happy to take any questions or. Okay, if not, I'll finish a little bit early. Sorry, I know this was a bit more math than we normally have, but hopefully you can go back and review the outputs. Sorry, the papers.
There's one left.
Okay. Oh yeah, there's something on Zoom. So I have a question on Zoom. The aggressive inference network learning. Yeah. Oh, so there was I can say this for everyone. There was a question on Zoom about the aggressive inference network learning, and basically what the aggressive inference network learning does is it takes multiple steps with the inference of training the inference network before it updates the decoder or the generation network. And the reason why this is useful is because it allows the inference network to identify latent variables that are useful for the generator more quickly, so that the generator doesn't degrade to a point where using the latent variables is not helpful. So the generator, the decoder, could just be a decoder that completely ignores the latent variable Z, and it likely will do that if the latent variables are not very useful. But by learning a useful inference network early in training, then that helps avoid that problem. So that's the general idea there. Yeah. Okay. So now we're done. Thank you.